Hello and welcome. In this short module we will learn digital modulation. We will look at amplitude modulation or intensity modulation of optical signals, and we will look at the simplest modulation in terms of phase called the binary phase shift keying. So, we will begin by looking at the transfer characteristic which we called of the modulator that we studied earlier. This modulator was the Mach-Zehnder modulator, and we know that the electric field input and the electric field output of this modulator was related by this cosine transfer function. The electric field output to the electric field input of the modulator, if I plot that against the difference signal ud of t that I was applying to the Mach-Zehnder modulator, then you would see that there is a electric field relationship written in the black color. This is the cosine form, and the red one is the power transfer function, which is the ratio of output power to input power as a function of ud of t. We have already seen the use of this Mach-Zehnder modulator to generate pulses, optical pulses out of continuous wave optical input signals. We will now look at how to implement basic digital modulation technique using this modulator. The technique that we have in mind is called amplitude shift keying. So, this A stands for the amplitude, S stands for shift keying. As I remarked in one of the earlier modules, this shift keying is a older terminology for talking about digital modulation, something that has been persisting even now. So, this ASK simply means that I have to switch my amplitude between two levels. Why two levels? Because to this ASK transmitter, let us functionally label this as ASK transmitter. There is of course the optical source which is coming from the laser or the laser diode, and then output would be the light wave which could be coupled, or it would be processed further and then coupled to the fiber after pulse shaping and everything. As one of the other inputs to the ASK modulator is the message signal that you want to transmit. This message signal will be in the form of zeros and ones. This 0 and 1 is an abstract quantity, but if I want, what I want to obtain is this light wave to represent 0 and this light wave to represent 1. This 0 and 1 is my information or data which is coming in as one of the inputs to the amplitude shift keying. In a real transmitter, this data would not be in the form of 0 ones, but this 0 would be represented by a waveform u0 of t. This would be represented by the waveform u1 of t. We will see how all these things are related. In amplitude shift keying, this is how we start. We say that when the bit 0 arrives, so this is how the bit 0 is there, and at each of these symbols last t seconds. So, the symbol rate is basically 1 by t. So, this is the symbol rate which is denoted by this Rs. T is the duration of one symbol. If you want, you can also put a S here to indicate that this is one symbol. The inverse of this Ts or 1 by Ts is called as the symbol rate, and that is denoted by Rs here. The mapping between the abstract data 0 or the abstract bit 0 and the corresponding light wave is that if I get a 0, then the laser light should be modulated, or the laser light should be changed in such a way by this ASK transmitter block, in such a way that it produces a signal which has a peak power of 0 light wave. Thus, if I were to graph as a function of time, a bit 0 is characterized by the laser light being blocked off for a duration of t seconds. So, this is the duration t seconds, and for this duration the light wave is simply blocked off, and E out must be equal to 0 during this particular time. When I get a bit 1, this bit 1 is characterized by sending an average optical power of Ps. An average power of Ps is what we want to send in, and this is equivalent of having an electric field of duration t, but then having an amplitude of square root Ps. Remember that E in is actually given by square root of Ps into e to the power j omega st or equivalently in terms of its real value, this is square root of Ps cos omega st, correct. So, this is the signal that I would like to transmit over the duration t. Okay. So, when I get a 1, I would be transmitting, and remember that this omega s is quite large. Okay. This is the electric field. Remember, electric field can be negative, but if you were to look at the power, then this power would essentially be a constant power, because what you would be transmitting is the average power contained in this waveform. Okay. So, we already know how to calculate this average power contained in this waveform, because in the previous module we have learnt that if I have cos omega st which lasts a duration of t seconds, and I assume that omega st is either some multiple of 2 pi or integral multiple of 2 pi, or that this is very large compared to 1, then if I were to perform this integral in order to find out what is the energy contained in this or what is the power contained in this, I will have to take this cos square omega st and integrate this fellow over dt, right. So, this was what I had done, and this would have given me t by 2. In this case, what signal I have is square root Ps cos omega st, which would last a duration of t seconds from say 0 to t, and this fellow would be given by t into Ps by 2. Okay. So, this is how I would be transmitting. So, when I have a bit 0, I will be transmitting 0 power, and when I have bit 1, I will be transmitting t Ps by 2, but this particular quantity which we have written is actually the energy of the signal. Remember that the energy of the signal is given by S of t. If S is the signal, then the energy is given by integrating S square of t over the duration t. If I were to divide this energy by time, what I get is the power. So, let us write down this as a different one. So, let us use a different signal symbol, because we have already used S here. So, let us say E g of t, where my signal is g of t, and this, if I divide the energy of the signal g of t by the duration t, what I get is the power Pg. So, in this particular case, I have two signals, one signal which will last from 0 to t, right. So, this is your signal. So, we can call this signal as S0 of t, or we will call this as S1 of t. S1 of t is a signal which lasts for a duration t seconds, and it is given by the value 0, whereas you have another signal which will last again the same duration t, but it has a power of Ps by 2. Okay. This 2, because this is the average that you are calculating, this is the average power that you are calculating. So, therefore, there is a Ps by 2. Okay. You can also define these two in terms of its peak power. This would be peak power of 0, this would be peak power of Ps. Okay. In some sense, you can talk of this as 0 or Ps. Okay. Now, what is the geometric interpretation of this? Well, you have two signals here, and incidentally these two signals can be defined by a single signal, which is cos omega st. I also know that I have to do this division by 2 by t. As per the previous module, I have to define this multiply this one by cos square root of 2 by t, so that this would form phi s1, right. If remember, s1 of t was cos omega t. In this case, there is only one signal. So, let me just remove this s here and then call this as phi 1. Okay. So, with respect to phi 1, I can represent bit 0 as 0 into square root of 2 by t cos omega 1 t. This is my vector having a magnitude of 0, and I have a vector 1 which can be defined as square root of Ps square root of 2 by t cos omega 1 t. So, if I were to send this square root of Ps signal, I have changed the amplitude of this signal square root of 2 by t into cos omega st. So, this is cos omega st. By multiplying it by square root of Ps, I know that the power here would be Ps, because this 2 by t will get multiplied by t by 2 when I take the power. So, that would be gone, okay, or when I take the energy. So, that would be gone here. Okay. So, if you are slightly confused, do not be. This what it means is that I have only one dimension that is sufficient for me to represent both bit 0 and 1, and if you look at in a slightly different way, this signal that we have written can also be rewritten by writing 0 sin omega st, or and then also write down this as plus 0 minus sin omega st, right, because this is the real signal which I am writing. So, this can be written as minus 0 square root of t by t sin omega st. So, it can be considered as a two dimensional vector, except that the second value would always be equal to 0. But since I have already written down the I and q planes, right, the corresponding I and q values here that I have, remember, if I have Si of t cos omega st minus Sq of t sin omega st as the real signal S of t, the I and q, in terms of I and q, the complex signal can be written as Si of t. So, this would be S bar of t, which is the complex envelope of this one, as Si of t plus j Sq of t, and in this case Si of t is constant, Sq of t is constant. Luckily for us, Sq of t is equal to 0, Si of t can take on two values, 0 and square root Ps. If I normalize these signals by saying Ps is equal to 1, then square root of Ps will become 1, and I can now represent bit 0 which is given by Si equal to 0 coordinate, and bit 1 given by Si equal to 1 coordinate by writing 2 points here. So, this would be my 0, this would be my bit 1. Okay. So, this is bit 0, this is bit 1, these are the actual values that I have used, 1 and 0. Okay. So, 1 maybe this is milliwatt or 0 milliwatt would correspond to the physical variables. Okay. And if I do not really worry about what this milliwatt is, then I can eliminate these units here. Okay. But whatever that is there, you have to distinguish between 2 points, right. One is that on this IQ plane I have actually condensed two waveforms. One waveform corresponds to 0, which is S0 of t, which is actually 0 for 0 less than t less than t, and then S1 of t, which you would be transmitting cos omega st, which would last over another duration 0 to t. So, I have actually written down S0 of t, which corresponds to bit 0, S1 of t, which corresponds to bit 1 in this geometric representation by choosing the square root of 2 by t cos omega st as the unit signal. So, in terms of that signal, this component is 0, this in terms of that would be 1. So, the coordinates of those in the IQ coordinate plane is given by this 0 and 1. Incidentally, this is called as the amplitude shift keying constellation, or simply the constellation corresponding to ASK. Okay. So, this amplitude is going from 0 and some value. Okay. Intensity is equivalently going from 0 and to some non-zero value. Therefore, this is also called as intensity modulation. Okay. One final point, I have arbitrarily chosen to send 0 when I get a bit 0 and a 1 when I get a bit 1. I can switch around. Okay. There is no harm. I can consider this as bit 1 and this as bit 0. After all, zeros and ones are abstract. What we associate with the waveforms is something that is real. This association can be in any way that you please. So, you can choose 0 intensity value, that is 0 milliwatt, for example, 0 power value, 0 milliwatt power to bit 0 or bit 1. Similarly, say 1 milliwatt power to 0 bit or the 1 bit. So, this is all up to you. This kind of representation of the waveforms which are actually being transmitted to represent the corresponding bits that you are receiving in terms of some geometrical pattern in the IQ plane is called as the constellation diagram. Let us move on from this intensity modulation. Now, before moving on, let me ask you, what should be the corresponding values in terms of the implementation of this one? Well, we have already seen that one. If my ud of t is equal to V pi, then the Mach Zehnder modulator output would be 0. When it is equal to 0, the Mach Zehnder modulator output would be equal to 1. So, if I want to actually realize this S0 of t and S1 of t in terms of the in terms of Mach Zehnder modulator, then I take in light from the laser diode and then send u0 of t, which is equal to the ud of t, whatever that value ud of t would take, and this would be equal to 0, or u1 of t as ud of t, which is the which is what ud of t should be when you want to transmit a bit 1, and this would be equal to v pi, and it would be equal to v pi both over a duration 0 to t, and what you get is S0 of t and S1 of t. Why should it be 0 and v pi? I have to switch these two because I associated 0 with 0, right. So, I have to make this as v pi and this as 0. So, when ud of t is 0, the Mach Zehnder modulator will simply act like will be biased at the maximum transmission point, and S1 of t will be equal to square root Ps e power j omega st. Here it would be equal to 0. So, this is essentially what amplitude shift keying or intensity modulation is all about. Okay. Now, let us move on to another simple modulation, and we will stop at this point because we want to come back and then combine these two in the next module. Okay. So, in this module we will look at one of the simplest modulation in terms of the phase called as the binary phase shift keying. The idea of BPSK is quite simple. If I have a BPSK modulator or a BPSK transmitter, I have to consider the light coming in from the laser diode, and I have to again have bits 0 and 1. I am denoting them with these quotation marks so as to emphasize that these are bits 0 and bit 1. What I should get is, if I get a bit 0, I should get minus square root Ps cos omega st. Okay. If I get a bit 1, my electric field output should be plus square root Ps cos omega st. Okay. What is the corresponding energies associated with these two? To obtain the energies, you simply square them and integrate over the time. So, that would be Ps t by 2. The same energy is associated with this square root Ps cos omega st as well. However, if I define phi 1 of t, which we had defined as square root of 2 by t cos omega st, then or equivalently in terms of the IQ plane, I can write this as 0 sin omega st minus 0 sin omega st. Then I can easily see that corresponding to this one, Si should be equal to minus square root Ps, corresponding to this, the coordinate Si should be equal to plus square root Ps, right. So, geometrically they are actually opposite of each other, having the amplitude values of square root Ps, and and the value here is minus square root Ps. Therefore, the length of these two are essentially equal Ps. Okay. So, in terms of the energy or in terms of the envelope, nothing changes, they are called as the constant envelope. What will change is this particular phase. Phase goes from 0 degrees and 180 degrees. Remember, we have defined this as bit 0 and this as bit 1. So, this is your basic BPSK modulator. How do I realize this optically? You remember the phase modulator that we talked about. In order to obtain minus square root Ps, what I have to do is to send in V pi. If I have to obtain 0 phase shift, I have to send in 0. So, this V pi will be equal to minus, this V pi will give you phase shift of 180 degrees, this would correspond to bit 0, this 0 will give you 0 degree phase shift, and this would correspond to bit 1. Okay. So, this would be the realization of the BPSK modulator using optical means, and this is the corresponding constellation for the BPSK signal. We will now combine amplitude and phase shifts in order to form what is called as the quadrature amplitude modulation, and we will begin this discussion on quadrature amplitude modulation in the next module. Thank you very much.